integrity reporting. So we have this Canvas site for the course, or not the course, but the topic, the group. We're working on ways to get people to sign up for it. I'll just keep a list of people's names that are interested and share information. We could have the registrar puts people's names into this and as a mailing list, and we'll see what we want to do at some point with that. So the thing I wanted to do today, besides answering questions if people have them about our application, is just show some extra data sets, a little more analysis, a little processing of variables, manipulating things to get things going. And so I've chosen some things that I think are interesting that illustrate some of the pitfalls or challenges. So to begin with, we're going to look at some data on baseball. And if I press the laptop, I'm going to use my own laptop because I don't run into restrictions in terms of read-write like I do with that might. So there's, that's there, right? So let's open that up. Right, so Major League Baseball has information on players and teams, and all the major sports would have these extensive files. All right? And so this one under Major League Baseball on stats has these players. This is in 2019-18. They've, I guess, set up 2019 in advance of the spring training that hasn't quite started yet. But for 2018, this is the entire season of data. And so look, there's all these numbers, the players, their team, their position, games, at-bats, runs, hits, and so on, and some other summaries. And so it would be nice to have those data in R to be able to use. Now there's some more sophisticated ways to do this that we might talk about later of getting these data. But one thing that can be done with a lot of different data sets is just, I'm doing this on my laptop, which I'm not so, I'm better with a mouse. But if you highlight these, and so I'm not going to do that here because I'm not so good at doing it with my touchpad. I usually use a mouse. But if you highlight all those, right, you can go to Excel and drop it in. And a lot of web pages, you highlight it, and it will drop in and reproduce like this, right? So I've done that before this session. There's 3 pages of this actually, so if you go to the next page, you get the next one and so on. And so then I went there and I added those in there. So I have all 140 some players in that Excel file. And to get it into R, I need to set my directory so I'm at the right place. And I happen to open this here, but if I was starting out from scratch and starting RStudio, it would be looking wherever the default is, or maybe the place you were last time, and you would want to change your directory. So under sessions, you can set the working directory and look for a location. And you'd want to look for the location that you put that Excel file. Now mine happens to be here. Say I just moved to that place. You can set this folder, set this thing as a working directory, and it's going to be here. So to get that Excel data set in, that's sitting there, this Major League Baseball version 1, right? One option is under File, up at the upper left, there's this Import Data Set option, right? There's an Excel option. So let's look at what that looks like. Right? So you do the Import Excel, it opens up this interface here, hit the browse, I'm going to choose this Major MLB Players version 1 and open it. And it shows you a bunch of information that's there. Right? It seems like it's picked up pretty much the variable names and the players and things looks pretty sorted and all that. Right? One thing I like to do with these things is give it a new name just to make it a little bit smaller. So Major League Baseball 1. So down here you can change the name instead of if you have a long name on an Excel file, it'll be a long name there. So you can make something shorter there. After you do that, here's a little trick. You have to click somewhere on the screen, right? And it will change the name that you're saving. Right? If you change it here and then press import, it hasn't changed the name yet, and we'll use the old one. So the series of steps here, I would browse and pick that file, right? And instead of using that long name, I'm going to make it smaller, right? And then I click over here, and it changed this little code preview for me. Right? And I'll import it, and then MLB1's here, and it views it, so it opens it up for you up here. Now I've gone through this once, so I have a few extra objects up here. But this MLB has these players information in there. So the Excel file is now inside of R, right, under that object. However, let's take a look at it. Right? There's a command called str, which is structure. It shows you something about the data set. Are things, what type of variables do you have? How many? What are some typical values? And if you do that for this structure one, oops, let me see if I can scroll up just a little bit to see what it looks like here. All right. It's telling the CHR means that all these variables are characters. Right? Well, those are numbers. I want them to be numbers. Right? But R has decided that those should be characters. MLB1 is a data frame, so you can refer to the different variables with a little $ in the variable name. So RK is rank of these players, 1 through 141. And there's some just kind of data manipulation things. Is it a character variable? Is .character of that? Yes, it is true. Is it a numerical variable? No, it's not. It's false. What do those things look like? There's 141, so you can actually look at them. It might be hard to pick out something just as that, but if you sort the values, one thing you see is there's RK at the last two entries. There are some letter entries in there. Right? What are those rows that have RK entered as the rank? One way to select rows is this command here. So MLB1 is a matrix. It has rows and columns. And you can select certain rows by putting something in the first argument here before this comma. And one way of picking is that variable RK equal to that RK word is the double equal sign is essentially asking the question, is it equal to capital RK? And if you run that, it looks like there's a couple extra rows in here that repeat the header. Right? So what's probably happened is as I copied the data from the web and pasted it into Excel, I got extra copies of the header. Right? So we can remove those. Right? We're going to assign our new Major League data, the Major League 1, but I'm going to take out the rows that have the variable RK equal to that character RK. Right? So the exclamation point equal means not equal to. And so I'm going to select those rows and get rid of them. So if I run that, now I have a data set MLB new. It has 141 observations. If I knew beforehand there's 141 players, that would be I'd be kind of keyed into that, because the original MLB had 143 rows, right? It had this couple extra where it repeated the headers, right? Yeah.
So it's telling me I don't have the read Excel, so I remember we had to import that from somewhere. What was the?
Did you go through this file thing up here and kind of import data set, right? And this Excel from Excel.
Oh, that's all.
If you go up through there, it'll do it automatically for you.
Oh, okay. All right, yeah, I just had to. I'm good now.
But it is a package, so it has to be installed with R. It's not part of the default, even though it would seem like it would be a pretty common one to use. But if you go up there through that import data set, it will do it automatically. Right? So while you're looking at things, were there some funny characters in that RK variable? There's a function called is.ina. It asks, is it a missing value? NA is missing entry. So is.ina is this thing missing? Or is it kind of a blank, like it's just a character, but nothing's in it. So you can do different things to ask, are there some anomalies in there? In this case, both of these things return the values of 0, so there's no, did I actually run this one to get rid of that? Yeah, I did, okay. Right. Now we can change that RK variable into numeric. We've taken out all the letters, and now there's just numbers. We still have to tell R that it's a numeric value. And so we do that. Now we can use functions like summary that summarize that numerical variable for us. Right? So we initially grabbed some data from the web, we put it in Excel, and we read it in. And there happened to be some variables in there that were characters. And so we discovered that. We found where the source of the problem was. We removed those errors in there, and then and changed it all to character. Now, that's only one variable, right? There's a number of these variables that are still character. So the rank, the RK variable now has the type that's listed there is double for double precision. It's a numerical variable. But the CHR applies to all these other things. Right? You could change a few other things to numeric. It turns out that it doesn't really want you to do things all at once. These other things gave me some errors. They didn't really work. You can do one variable. Yeah, it didn't like these other ways of doing things. It does like it with this $G. So if I want to change the number of games that they've played into numeric and then make a histogram of that, that one worked. And so I get the number of games that players played. There's 162 games in the regular season, plus playoffs. Those players might have a few more, but that's the distribution there. So we could go through and change others, variable by variable, but that's a little bit of a headache. Instead, we might want to go back and fix the Excel file and read it in again. Sometimes it's just as expedient to do that, and then the problem's fixed in the Excel record as well. Right? There were a few variables that also were a little problematic. One variable was 2b. Its variable name was 2b for getting a double, 2 bases from a hit. R doesn't really like variables that start with a number. They like to start with a letter. So you can reference it, right? If you type just the 2b as that, it says it doesn't know what you're talking about and gives you an error. But if you do, kind of in quotes, the 2b, then it gives you the numbers. But you can go back and fix those. So we're going to remove the extra rows and do a change of a few columns. And so I made a new version of my Excel file. And if you go down some, you can find the places. So if we go back to the first one, right? If you go down a little bit here, right? So here about row 52, right, is the repeat of that header column. So if I get rid of that, right? Up here at the top, there were some of these columns, 2b, 3b. There's this other one, average, which has a little annotation note in Excel. Right? It was an annotated note on the spreadsheet on the web, and it became an annotated note in there. When you read that into R, it gives you a long variable name that you wouldn't necessarily like. So in my modified one, I changed that, overwrote that, just calling it simple average. And then I changed it to double and triple for the hits. Just gave them new variable names that I like. Right? And I'm going to read that in. So again, I'm going to go up to the file, the import data set from Excel. Then I'm going to browse and pick the version 2 that I've saved. Oops. Okay, that's it. But I'm going to modify this thing MLB2. right? So I get a shorter name and import it. Now if I do my command, little structure in LB2 on these things, it says these things are all numerical as outcomes, right? So they were numbers, the entire column was numbers except for the header, and so it read it in as numbers. So things I might want to summarize then will work out well. So that's in there. So I can do, say, a histogram of the average, right? The batting average is as a percentage, as a decimal, 25%, 30%. Top players going a little bit over 30%. We could look maybe at the players who got better than a batting average of .32. In baseball, they often say 320, right? Out of like 320 out of 1,000. And so you can select rows with logical equations. MLB2, the range right there. So there's a few people, Betts, Martinez, and Yelich, 3 players, 2 from Boston, right, that had batting averages. It doesn't say all their values there, which is a little annoying, but you could look at them. These are the top 3. So what happens if you do? Just curious. MLB2, the first one. What is that? Betts. Okay, I have to look into getting all the variables there. In any case, you could do other things like the range or sorting the averages to get that. Say you wanted to divide the players into categories based on their batting averages, kind of low, medium, and high. Right? There's a command in R called cut, which will cut a variable along different division points. Right? So you give it the ranges going from below the lowest value you'd want up to the first cut, and then the distance to the next cut, or the interval to the next cut, and so on. And if you make a table of that, it's going to cut the batting average ranges into these things. And so you get the players that have lower, and then a couple in the middle, and a higher end batting averages. Right? You can actually save that information about what category they're in by creating a new variable. So the MLB2 is a data frame. Right? You can add a variable onto it by just putting a $sign in a new variable name, like average cat, like for category, and I'm going to assign the cuts that are there. What do those look like, the cuts? Let me see if I can, well, we'll get it in just a second. So that's assigned it, and if I want to look at a few players, like players 1 through 3, player 50, and player 100, in terms of their average in the category they go in, right, that will show me, so that there was some averages, right, and then the category they're in. The top 3, this is arranged in numerical order by batting average, actually. So the top 3 are in the first 3 are in the top category. Go down to player 50, that person falls in the second category. Player 100 falls in the lowest category. So you have this tabulation of where they are. But now that we do this, right, there's different positions in baseball. Right? Do you know, not every player, every player, positions, players tend to perform the same on different things. Right? They have their specialties. So I want to summarize some of these variables. So instead of typing MLB2 $sign and then the variable name, one thing you can do is attach it. You can attach that data set. Right, so this tells R to look for variables you might be asking for objects as variables that are on MLB2. Right? So it adds it essentially to the search path where it's looking for certain names. So HR, I don't have to type MLB2 $sign HR after I attach it. If I just type HR, it's going to look through everything it has, and HR will be something that it will find. So what are home runs? HR is home runs. 2 to 48 home runs. That's a histogram of home runs by player. Box plot is another type of plot for displaying a distribution. So here's a box plot of the number of home runs. Again, ranging from about 2 up to 48. The median here is about 20. And it looks like there's one player that really kind of stuck out in terms of more. But let's divide these home runs up by position. POS is a variable name on that data set. I can just look at all the, POS, all the positions. That's how they're denoted. Right field, left field, second base, center field, first base, and so on. We can tabulate those to see what they look like. Right? 20 first basemen, 21 second basemen, 18 third basemen, 6 catchers are on this list, and so on. This little option up here is use in A equals A. So if there's missing values, they don't get tabulated by default. Right? So some of these players were in there, but they weren't designated, and it wasn't written in what there was. Like if there was a manager, somehow ended up in this list and didn't have a player designation, and it was missing, they wouldn't show up in the total, even though they'd be in the data set. You could force it to always use the NAs to create a little category over here. In this case, it doesn't matter as much because they're not missing, but anyway, you can. Split is a nice little command, right? It will split one variable by the values of another variable. So this example here is going to split the home run values by the different positions. Right? Technically, it creates a list with all the home runs for the shortstops, then all the home runs for the first baseman, and so on. And if you do a box plot of those things, right, you get a box plot by each position. Right? So which positions are doing the best in terms of home runs? Which players are most likely to hit home runs? Right. The designated hitter, the DHs, are pretty high. Third base is pretty high. First base is pretty high, and so on. Looks like there's just maybe one person that's OF for outfield, not specifically left field, center field, or something like that. But that's a lot of categories. Right? This is kind of 1, 2, 3 is kind of a pretty good thing, but it's possible to change the order that things get reported in. That there's 2 related types of variables. One is called a character variable. That's just the letters. But another one's called a factor. And a factor can be character variables that are in a certain order. Right? So you can tell R what order you want to use. Is it a factor? Right now, no. It's not actually a factor variable. Is it a character? Yes, now it's a character variable. I'm going to detach that Major League Baseball thing because I'm going to add variables to it. So I don't want it to be kind of fixed in time. I want it to change. So you can search shows you all the things that are looked for when you type a command. Right? And MLB2 is there because I attached it. So I can detach it. Then it's gone from my search window. Oops. And if I do that command again, it's no longer there. And then I'm going to create a factor. I'm going to rename the position variable. I'm going to make it a factor variable. And I'm going to tell it what order to put the levels in. Right? I'm going to put the designated hitter, and then the center, the catcher, and then the first, second baseman, then shortstop, because on the field, the shortstop is between the second baseman and the third baseman. Right? And then left field, center field, right field, and then just outfield. I put them in that order because I like that. When I do the table now of those numbers, it gives me the count in that order. And if I do a box plot, it gives me the box plots in that order, which could be nice for trying to understand things going on. But that's a lot of categories. you might want fewer categories. So let's make an infield outfield designation. Right. This particular data set doesn't have pictures in it, which if the picture's in there, they are kind of a whole different issue. So to create a new variable called infield, first I'm going to call everybody in. Everybody's going to get that, right? So it's just one character string there, in. That's going to be everybody. Right. Then I'm going to replace the positions that are other than that, other than infield, as a new designation. Right? So I'm going to select them and give them a new name. So of that Major League Baseball infield, I'm going to take the ones who have their position is in this list here. Right? That's kind of another flexible way of selecting certain individuals. Right? So if its position is DH, left field, center field, right field, outfield, I'm going to call it a new thing, which is out DH. Now you could debate where you should put the designated hitters. Should they be counted in the? Should they be counted at all in comparing infield to outfield? And so, depending on how you would make that split, is a subject matter choice that would affect the analysis. But we're just going to make one choice here. So run that, run that. Now when I table infield, I get 85 infielders and 56 outfielders for designated hitters. If you do two-way table, by that variable, by the others, you see how they split out. Right. I'm going to attach my MLB2 now again, and then do a box plot of that, and I get a box plot of infield versus outfield. Not too much difference there. Right? So is there a statistically significant difference between these two designations, infield versus the other, in terms of home runs? Right? That could be answered with a t-test. This little tilde here is another way you can sometimes write models in R. So a y variable tilde x. So y is a function of home runs is a function of infield. So I'm going to do a little t-test here. I'm going to take out the designated hitters. I don't necessarily want them in my data set for this test. I'm going to do the t-test that has equal variances. So there's some options that come to some of these things. Now if I run that t-test, that's my box plot again, I get some output that gives me the basic results for a two-sample t-test. The average in the infield was 20.15 home runs. The average in the outfield and designated hitters was 21.43, so it's a little higher, but a 95% confidence interval for the difference. Straddle 0, which would be no difference. So no difference is kind of a plausible possibility here. The t-statistic is given, degrees of freedom for the test, and a p-value. P-values of 0.3 are not significant, which suggests that there's not any conclusive evidence that these groups are different. They might be the same, essentially. There's a couple other ways that people might approach that. You can do a linear regression with an indicator for its infield. You can do analysis of variance with dividing the group up by whether it's infield. The ANOVA is the most similar to that. And these things are all under the equal variance assumption. They all give the same p-value. They all give the same result. But just depending on the application is doing a little more. So we've tested that, right? Now what R does with some of these tests is kind of interesting to see. So is what it actually does is when you do one of these t-tests or linear models or ANOVA, is it creates lists of things. It has to do a lot of things to do a t-test. It has to count observations, change that to degrees of freedom, get means, get variances, compute t-statistics, standard errors, p-values. That's all stored. Right? It does all that and it puts it together in a list. Right? So if you have, I'm going to do that same test command again here, but I'm going to save the results as something called myTest. I just made up myTest as the placeholder for that. Right? Nothing special about that. So myTest does that. Now what's in myTest? MyTest is actually a list of things. These are the things that are in myTest. There's a t-statistic, the parameter value, p-value, confidence interval, estimate, and so on. So that stuff is all there. And so you can reference those other individual things. Right? So if you wanted my test, p dot value, that 0.43 p-value comes. So one place you might use that, say you want to make a box plot, and HR as a function of in field, right? You can put, make little descriptions here. So let's say I want p-value is, and then do my test $sign p dot value. And that's close. Right? It will put that p-value thing up here at the top, and so you can annotate your graphs a little bit more. That's probably too many decimals to be reasonable. So let's say I round this thing to 2 decimals. And I need one more bracket. So the p-value for testing between these things is 0.43 as they're on the graph. But yeah, you can pull out a number of things out of that. So that's kind of the example here. If I wanted to write the entire data set that I've been created to my file so that I can share it or something, of course you can save the image here, R2 in class.rdata. Right? So I can save it as an R object. Okay, so I have to press run, get that to go down there. Right? So now I've saved the R object, but I could write it to a CSV file, and I'm doing MLB2 as the data set. Now I'm going to call it MLB2.csv, and there's an option here, row.names. I don't want the row names necessarily to be in there. That one's optional, whether you do it or not. And so that will create a file over here where I have my R2 classes here, my MLB2.csv, and now I have those data sets that I can move around or reference other times. All right, so this has been one example. Right? We got the data off the web, we had to do a little processing to get it to work, we created a few other variables, and we got some analysis. But any questions about those things? One other place that I've seen variables that are supposed to be character end up being quantitative, but end up being character, is if the variable that's recorded in some survey analysis is female or male or yes or no, and they're mostly supposed to put in 0, 1 or 1, 2 or something like that, but every once in a while somebody types F or M or Y or N, and so they're entering it in an Excel spreadsheet maybe, and it's a big thing there, and they just haven't done anything with it. There's not any way for them to know unless they scroll through it and look at every variable. And they might have entered 50 variables. And so the possibility of one error showing up in there is really happens. And so if you see, is something numerical, is it character, it could have, it's a quick check. I mean, it's a check that's important to do for some analysis. So a second example. Right? We'll look at a data set it's actually used in the book that we use in Statistics 120. Here's my little thing with some data sets. This thing on Florida lakes. And that's just an Excel thing. And so this has an ID, a lake name, alkalinity, pH, calcium, chlorophyll, and so on, and mercury. So that's just a CSV file that's already there. One way to get that into R is just to, my current working directory is here. It's actually in the sum data sets place. To get that, I don't actually have to change my working directory to that location. You can reference the file locations by writing a little code here. So it's called sum data sets is the file, so sum data sets, and then it's this kind of forward-leaning slash that needs to be used there, and then floridalakes.csv. So you can type that directly and just get it into R. If you do that, you get this thing called lakes, right? You can look at the names of the variables on lakes. Up here in the environment, lakes is there, number of observations, number of variables, the variables that are there. Essentially that's what come out of the structure command. Head gives you the first 6 values for these variables, and so you see some of the things that are there. Right. So we're going to imagine that we've got this data, and now we want to predict average mercury based on some other variables. Right. So this is just going to be an example of building a statistical model and getting a little bit of output from it. Right. It's something that we would study in linear regression, right, as a method. So a number of these things are quantitative. R has a command called pairs. I'm going to make the graphic window over here as big as I can to do this. Now the lakes variables 3, 4, 5, 6, and 7. So 1 is ID, 2 is lake, 3 is alkalinity, then 4, 5, 6, and 7 is the average mercury. Right, so these columns, 3 through 7, I can refer to in that way. Right? So again, it's rows and columns. So the second thing after the comma refers to those, and 3 through 7 is that. So if I do pairs, I get a plot. It's called pairwise plot. And so it takes each pair of variables, like alkalinity and pH, and the one that's, if you map alkalinity over here, that's what's on the y-axis. pH in this one would be on the x-axis. So as pH is going up, alkalinity is going up, and vice versa. So what we're going to try to predict is down here in the lower corner, this average mercury. And so that range is over here in this area. And the thing that would be on the horizontal here would be the 3 variables. Right, so alkalinity to predict mercury would be this lower left. Average mercury versus pH. Yeah, so there's some relationships in there. This would actually be kind of a difficult problem because things look kind of nonlinear, and there's a few lakes that have very high chlorophyll, very high values of other things. So those points in a linear regression are called influential, and they cause a little difficulty in trying to do good predictions. But this is not really about doing that and teaching those methods. But doing a model in R for that is writing a statement kind of like this one here. So this is an LM for linear model. So that's a lowercase l, not a 1, it's hard to tell. And so the way that models, kind of like those box plot commands, we have our y variable and then a tilde. And so y is the response, and then everything to the right is the outcome. And you can put multiple predictor variables in there separated by the plus signs. So we're going to fit a model that tries to predict average mercury based on alkalinity, pH, calcium, and chlorophyll. The command ends by telling it what data set to use. So we're going to use the data of lakes. If lakes had been attached, you don't necessarily have to tell it what data set to look. It's going to look for those variables in there, but I haven't attached this one. So if you do that, this thing saves what is going to be called model 1. Right? And if you summarize that object, it gives you this regression output. Right? It tells you what call or command you did. It gives a little summary of the residuals, which are important at looking at in regression. But then it gives you coefficients, an estimated intercept, and then slopes on these different variables. It gives you standard errors of them, t-test statistics, and p-values for testing them. And then other output that's relevant for a linear regression model. Right? The multiple r squared is kind of the percent of the average mercury variation that you can associate with these other variables. So about 45%. Not huge, not 95%, but it's non-trivial. So in a regression class, you go through in great detail what all this means and these things. But that's fitting a model for that. Right? Out of the model, that model, like the other T command, has a bunch of these things sitting on it. You can actually pull off these different things and do things with them. Make graphs, make confidence intervals, and so on. The coefficients give you the coefficients that would be in this linear regression line. You can also summarize that, and the summary of a model has a bunch of things in it. The things that are in the summary are a little bit different, but residuals, coefficients, R-squared values and stuff. And kind of behind the scenes, when you summarize or print these things, R has ways of presenting these things on the screen. So that's why you see it in a certain format. But say you wanted to get the coefficients from the summary. So here's that matrix of coefficients out of there. If you wanted to get the p-values on those coefficients, you could select it from that matrix. So it's very flexible. You can pull out these different things and possibly use them for something. Within modeling, of this, the pH, not all these variables are statistically significant. It's possible that some of those are not really helping us, given that the others are in there. So there's some utility for updating models. If you wanted to take out the pH variable, there's a little syntax for doing that. Now our model 2 does not have that variable in there. The R-squared has gone down a little bit from 0.45 to just below 0.44, but we have one less variable. It's not as complex of a model, and there's some nice thing about that. With these different things, there's ways to do plots. So one plot we look at in regression is called a residual plot. Fitted values versus residuals here. Generally, you want these things to be a random scatter. There's a little bit of deviation from that, in part because of the the pattern wasn't completely linear in the model. You can keep going with this. You can take out another variable and summarize that. And now we have just two predictors. Both of these predictors are significant. The R-squared has gone down a little bit more, so it doesn't predict as well, but it's only two variables. So, or there's things to do where you can add square terms and be make it more interesting. But I don't think I'll go through all of that. But the idea is that for different techniques, t-tests, linear models, there's quite a repertoire of things that are there. Getting the basic results that you might get out of something like SPSS or Minitab, it doesn't present it maybe quite as in such a pretty package, pretty way, right? But all that stuff is there, and then you can do a lot of other stuff with it. So that's kind of what I was going to do with that example. Another type of model is called a generalized linear model. One example of that is called logistic regression, to predict a 0 or 1 outcome. So the data that we're going to use here is some, it's not real data, it's all fictitious, but it's based on data that I had a project here at St. Michael's with the alumni office on recruiting individuals to consider doing donations to St. Michael's College. So they were interested in predicting what characteristics of people were predictive of the propensity to join as major contributors. So to get this file, it's called it's a CSV file. You can get CSV files also with this import. You don't necessarily have to do the read in. I wanted to look at this just to see what the interface looks like when you read one of these in. So if you go to this first one over here, it's under the file import data set. Right? There's this text-based thing. If you do that, it's going to ask you which one you want to do. I'm going to go to the sum data sets, and this is HC here. This particular Heritage Circle data set was based on a simple random sample from a very large database, so it's a small subset. And then the data were distorted, so it's not actually, no row is any one actual person. Right, so I'm not giving away any person's private information. This particular interface looks like this. In the comma-separated file, it's separated by commas, that's the input. Right? And then it has divided it up pretty well to make it seem to identify the headers. If you didn't have this thing collected here, it wouldn't understand that HC is a header. and so on. So it would replace it with V1, V2, right? So you don't really like that, right? So we can do that. If the separator had been a tab or something else, or semicolon or white space between those, you can change it so it can be flexible for your file. It looks like it's okay. So it reads it in and then it views it, so you can kind of see that it's okay. This particular data set has some variables like activity count. So for instance, like the histogram of the HC data set. Oh, I didn't change its name, right? Let me try that again. So file, import data set from base, and I'm going to go to this HC again, right? Everything looks okay, but see up here I can change the name, right? So I don't have to type that long thing. RStudio is neat because it will do the command completion, so I can have long names and it's not quite as burdensome. But if I just make it HC, then it's I get it there. So HC is now this short thing. The activity count that's on there, right, is pretty skewed. Right, this is a count of activities that different alumni have participated in at St. Michael's, whether they come to reunions, whether they do sporting events, all sorts of different recruitment activities and activities on campus. They get tracked on something. So this is really skewed. Right? So to make it a little more reasonable to do, you can take the logs of some of these things or transform them. Log HC. Let's see, and get the log of these values. On the log scale, it looks a lot more. Right? So the analysis of this, I had actually taken the natural logs of these activity counts and considered using that as a predictor instead of something so skewed. Right? So where are we in this R script over here? So now that that's in there, we can look at these a little bit. There's these variables are there. Here's a summary. Summary actually will summarize every variable in there. So for HC, it's a 0-1 variable, so it's a little bit less interesting. With such a low mean, most people are not in the heritage circle, and then a few are. Activities, log activities, you get descriptive statistics there. There's 18 people who have been reunion volunteers in this data set, and 182 that were not. It's about 10% or 9%. This HC variable is 2 and 1. So it's not the best idea to try to predict something that's so rare. It just does not work so well, generally. But the way you would do it in a larger data set is this thing called GLM, a generalized linear model. And again, the form of the model is specified much the same way. HC as a tilde and the name of different variables that you might use in the data set. The generalized linear model, you tell it a little bit more. You tell it what distribution family it's going to be using. Right? And the one that it needs for logistic regression to predict a 0-1 outcome is called the binomial family. Technically, there's a link associated with this that links the expected values to the predictors, called a logit link. Think about thinking like log odds as a function of data of your predictors is what it's doing. But if you tell it binomial, it by default takes the logit link, so you usually don't have to do that. If you do that, there you go. Saves a object. You can save an object there. You can summarize that model here, and again, within the context of logistic regression, which is something that we would talk about a little bit in Statistics 351 and more so in Statistics 451. You can have prediction of the 0-1 variable. And there's coefficients. Now, since this data is artificial, there's not much that's a significant predictor, and I wouldn't try to associate anything with that. But in the real analysis, things like age are important. the older somebody is, they're more likely to be one of these significant givers. The more activities they've done, if they're reunion volunteers, those things that you would expect to be predictive are predictive of being in that category. The point of doing this analysis would be that, instead of just having one variable or kind of ad hoc, trying to figure out who would be likely to be interested in this, you could make a prediction based on many variables and hopefully do a better job. There's certain functions for pulling out different model comparisons things. AIC and BIC are two specialized things that get used for comparing models. Age category. Right now in this, so there's this age, something called age category. And that's in the data set. So instead of using age, you might want to use age category. Using age in a model like this implies a certain particular relationship, a certain linearity. Instead, maybe you have an age category, right? If somebody's less than 65, they probably have not retired, so maybe they haven't retired, and they haven't been thinking about donating their money kind of into, end of life giving types of things. But after a certain point, maybe they're thinking about it. And maybe it's not a linear change with age, but more of a jump. So instead of putting age in there, you might put an age category. However, this age category variable here is actually numeric. It's 1, 2, 3. So if you put that into the regression, you get a linear effect on that age category, 1, 2, 3. And so that makes even less sense than actually using age. So you can change it to a factor. Right? So if you table just HC age cat, you get 1, 2, and 3. That's not so crazy, right? But you can take the mean of that. It is a quantitative thing. But what does a 1.345 mean in terms of this age category? Is low, medium, and high? It's not clear what that really means. Instead, if you create a new variable called age category, it's no longer numeric. The table looks the same, of course, as before. But if you put that one into the models, you'll get kind of a different effect. Instead of going through too much more of this for time, I'll just say there's a few more commands in there for different plots, and you can do different things with the model. At some point, kind of intermediate through a long series like this, it's good to save the output, and so that's just a reminder to do that. A few other small examples. Right? Sometimes you want to get data into R, but they end up being very messy. Right? And so I worked with some individuals in speech and hearing at George Washington University on some projects, and they gave me this data set. Get this thing open. And so these were data on children. I don't have names or addresses or any way to contact or isolate. I don't even know what city these people live in. Right? And this is the data set. Right? That there's individual numbers, cochlear implants, CI numbers, and so some different subjects. Right? Date of birth, I'll probably take that out, exam date, age of the exam, and then a bunch of variables, right? So number of correct attempts, right? And then a variable, this is about how children understand and perceive and reproduce sound if they have ear implants and were born or became deaf. Right? There are two ways these children get evaluated: Olim-SAC and Vid-SPAC, speech recognition, different things. They use those at they do different tests based on what age the children are, right? Different ones are. It's easier to tell an older child to ask them questions. Did you understand something, or to do something? It's harder to ask an infant some of those same questions and interact in the same way, so the tests are different, right? It might be a sound like a pig, and then pictures of farm animals, or something, or the word, they say the word, and then there's a picture, and then they try to identify that, right? And so if they're understanding, then they get it, right? But if they're not understanding, they don't. But I bring this up just because, imagine getting these data into R. Right? Well, there's kind of column headings down here somewhere. There's some information that's included in color in here, right? There's the same pseudo head in each of these that is repeated. There's some things that, like production, sound production at visit 1, that really pertain to a bunch of columns. So I would like to say that there's a neat way to read this and tell R to format it. But I think that for things as complicated as this, you basically have to redo it, right? And give it variable names, right? And this goes on. There's more visits. And then it says up here, data was verified, right? So that's a text sequence in there. If you try to read that in from this, it's not going to work out. This database is, is great for recording the information, right? Not a statistical database for analysis. It wouldn't really work. It'd be difficult in anything except just reporting these percentages out, right? Then there's another perception on visit, different group of variables and so on. It just keeps going. Then there's some people that are missing some things, and that's in gray. Not administered given VSEC, so there's another comment stuck there in the middle. Right, if you read that in, it's going to give you all sorts of things. Right? So unfortunately, for something like this, there's not much choice but to reformat it and make it. If I was going to, when I did some of this, so I create a new version of this. I just made this other version. So when I made a version of this, right, you can give it different names. So it's enough of a name there that I can figure out, talk to them about what it is. So there was all these nasal, so that's a type of nasal sound. Is it doing something there with production of speech? Consonant, something, consonant production forward, is it producing sound in the forward part of the mouth? And all these other things. So I could make variables. So X was the number of successes, N was the number of trials. So I could make variables that were more meaningful to me, but it was just a matter of, and then there was some missing values in there where they didn't do that. So it was just necessary to recreate it, to read it into R. And it just, when you deal with real data, you get this all sorts of messy things. Sometimes R can help you find those things, and sometimes you just got to go back to scratch. So anyway, not much else to say about that one in terms of analysis, but that's just kind of reality of some things you might get. Let me see if that'll show. No, I don't want to say that. So let's see what else is there. There's a couple other examples in here we could look at, but the nature of them is you import a data set and then look at some of the variables, maybe getting a new variable in there. Is this person a performer or not, representing it a few different ways. Maybe summarizing things about those performers by category. There's a data set in R about the states, the 50 United States in 1977, about different types of variables. It turns out that these variables are stated sort of as a matrix and not as a data frame. A little more convenient to deal with data frames. So it's pretty easy just to make it a data frame, and in fact you can add on more variables and put things together and name them and get a nice big data set to look at things. And you can look at information on Vermont. You can split it by standard deviation. Let's look at this one data set here. So I won't spend too much time on these, but you could look through them. So There's a bunch of data sets that come with R. They're used to illustrate some of its examples. They may be used in early textbooks on R and S+. They're freely available and can be used for different illustrations. There's one about the states. It's a help file for these things, US facts and figures. X70, so X77 here, 50 rows, 8 columns, statistics for different things, like population 1975, per capita income 1974, and so it has this thing called frost, oops, but it doesn't like to be referred to that way because it's not a data frame. You can refer to that frost1.xx70, right, just by putting it in quotes. It will allow you to do that. So these are the number of days during a year that you typically get temperatures below freezing. And so Vermont, 168 days a year, we get something below freezing. So that's right. So 168 out of 365, right? About 46% of the time that we seem to get some temperature below zero. But if you put all these things together, there's state abbreviations, measures of state center and regions and things like that. And now I get all these bunch of variables together. Oh, it's gone ahead and done a plot for me. There was one that was negative longitude and then latitude. If you actually plot those points, the state centers, it kind of looks like the United States. If you imagine an outline. These two up here are Alaska and Hawaii, so except for those. You can look at the information for Vermont. Now this was 1970s, right? So we're talking 50 years ago. Incomes double every, I don't know how many years or so. So if the average income was about $4,000, then you double, quadruple, multiply it by like 8. You're up to 32,000, something like that. So it seems very shocking to earn $4,000 a year, but many people earn $4,000 a month now. But if you think about the compounding of time, it really does. This split variable, to split it into things, there's a command called sapply. Right? And so this applies a function to different parts of a list. So if we want to split the frost variable by region, we can summarize it. What this will do is in each of those regions summarize that variable. So the north, east, south, north, central, and west. Apply is a different version of that. It will just work on the different columns of a matrix. Or rows. So ST 1 through 7, these were quantitative variables. The second dimension of that is the columns. If there was a 1 there, it would be the rows. Sometimes you want to summarize. If I had all those children in that previous data set, and I want kind of an average score for all the children, for each child, I could put a 1 there, and we do it by row. But this thing will give me some summaries of population, minimum, maximum, and other things. But the default summary command in R only gives you so much, right? And I want standard deviation and some other stuff. So how will I get that? Well, I could, right, repeat this command and put some SD in here and get my standard deviations and so on. But it's not quite as neat, right? I'm not sure what I wanted to do with that. So it's possible in R to write functions. So a function is written like this. So my summary is going to be the name of the function. And the thing that it's going to do is take in an argument x. Like I'm going to give it a row or column or something like that. And what it's going to do is it's going to include the summary, the standard deviation, the interquartile range, and a couple quantiles for me. All of x. And it's going to save all of that as something called out. And then at the end, it's going to just show me out. I wouldn't necessarily have to save it as out. I could have kind of omitted that, but you can kind of save things and do things intermittently. And so that's going to be a function. So if I run that, now my summary exists there. Let me get down here. My summary, right, is a function. If I don't have the parentheses, it shows me what the command is. Right? If you put something in there, like the frost variable, right? Oops, I need to run it. it will apply that function to the frost variable, and it will give me the summary I had before. Now I have standard deviation, report forward range, and I get more information. Right? So modifying functions or writing functions to do specialized things can happen pretty quickly. Right? And then I can use them in things like apply. So if I want to do my summary on all 7 of those variables, instead of having summary here, I can put my new function there. Right? So if I run that, maybe I'll make it all fit on one. Let's just do 2 through 7 so it fits on one page here. Now I have all my statistics, standard deviation, and quartile range, and set for all these variables. So I've added that pretty quickly to that. If I save that my summary, or rewrite it or something, it's something that can get used over and over again. None of the frosts are missing. Right. One of the frosts is actually 0. Where is that 0? I kind of went to the next one. So you can select that row. It's actually Hawaii. It has no frost. Where are the areas that have less than 20? In selecting different rows, you can do logical things. Like you can say, is the frost less than 20 and is it in the south? You could change it. So you could have, say, that the frost, you can do logical things. So it's not the case that frost is less than 20. And is there any place in the south that does not have the frost below 20, that has more frost? Right? That's this thing, if it's right. Oops. There's a lot of places in the south that do get a little more frost. So Maryland, Kentucky, Delaware, they do have some freezing weather. More than I would have thought, but the south, I guess, there is pretty broad. So that's essentially that that example of that. So in this one, there was this sapply, apply can allow you to do a function repeatedly, right? Pretty easily. You can write your own functions for things. So as anyway, that other one just does some other variables. There's one. So the last thing on there is just a data set from Professor McCabe. So he did provide, actually for the introductory statistics, the biostatistics class, we looked at some of his data. We'll just finish up with this example. So write an Excel sheet that had information on streams, the raw data. Looks like the stream name, sampling technique, and measurements of insect abundance. How many insects are there, and insect richness. How many different types of insects are there. And there's a few different streams that are there. In the first part of the data set, on the first sheet here, it summarizes what it is. He prepared this so that he could share it. This information was gathered by his students at St. Michael's as part of his classes. And so here's the raw data. One option for getting this into R would be to take this raw data and just save it as a CSV file. And you can save just that sheet and just have that sheet there. Right? And maybe do something about cut out that extra row there, make it all nice. So that can be a fairly quick way to do it. So if you just save that sheet, cut out that row, it's something that should read into R pretty quickly. I actually took out the space in the names there, so you don't end up with it trying to, any confusion, no complications for it. But I believe if you go to this Excel import, we might be able to, so file, that's what I want to do there, file, import the data set, and let's look at Excel. If we choose that one, so here it's in this some data sets, and the original one here. It's an Excel workbook. Okay, so it's doing that. That's not what we want. Sheet. We can pick which sheet. We can pick the sheet of the raw data. Okay. And then it seems to have done, even though there's that one empty row, it seems to have done the right thing in terms of skipping that row and then reading in data. So that's pretty smart, right? That's pretty good. And it's using these as headers, right? And I changed this little name here to bugs, right? To make it easier. Click here and it changes that. Looks okay, so I'm going to run it. And it looks like it did it okay. So if we had that Excel sheet, we could read it in even though there was a little more complication to it. Now I'm just used to looking at things. So there's the sample technique, this character, the stream name, and things insect abundance and richness. Right? So you could look at a box plot, one box plot, say, of the insect abundance. So this is where these long variable names are a little bit of a issue. So let's attach the bugs data set and then do a box plot of insect abundance. So once I attach it, it lets me use my little command computer, right? So that thing as a function of stream name. Stream name, good. And the data says attached, so I don't actually have to do anything else. So that's an insect abundance. If I want to keep track of this, I could put a label on that, abundance. So it looks like there's not that much different. These streams all had bugs. Maybe a few more at Potash Brook. But insect richness, this other one, oops. I have to change. Now is it going to insect richness? It's not going to, let's go back to the beginning. So
I think it's because it's a lowercase.
is it lowercase?
Yeah.
Oh, it's the first letters were lowercase. But in terms of insect richness, there's a real difference there. A statistical method for comparing three groups is analysis of variance. You can do that in a linear model. Insect richness is a function of stream name. And it does a statistical test. Is there a systematic difference by stream name? And it gives this p-value that's actually a very small number, so highly significant. So the graph really says it all. There's a difference in richness. The statistical test really confirms that it's highly significantly different. And it looks like non-trivial numbers of insects there. So once you have that Excel file, you can get it into R pretty quick and do some graphs, some statistical analysis to do a report. But so anyway, today we covered a few more examples of importing data, a few examples of manipulating data, a few examples of how models go. But really, it's pretty rich and pretty flexible for things. But yeah, that's what I was hoping to do essentially. So, but any questions? Anything you want to know about? I mean, it takes getting used to doing things in R. It's the more experience you get with it, it builds up. Right? It's cumulative in terms of experience and programming. And is there anything you'd like to see that you can think of off the bat for the third session next week? I mean, we could look at a little bit more programming. Every once in a while, I need to do a little more programming. And so that's a little more keeping track of indices, a little more careful use of loops, a little more careful use of indexes to select things. So maybe we'll look at a few examples like that, and maybe just look at a case study of trying to do something. For one of these, one survey that I've been involved in, there's a whole series of computations that have to be done. And some of them are selecting special subsets out of a big group, and then sampling, and then from different groups, and then appending it all together, and then so maybe we can make up something out of that related to, because it involves a few different steps. So, or maybe I'll figure out how to act. I think that there's probably better ways to get. I know there's better ways to get some information off the web. I mean, there are some packages in R to kind of scrape the web, but I've not seen one that's really pretty, right? So there's ways to read in the source off of a web page, but then you kind of have to know the code that's used in the web page before that. So you want to get the batting averages, you need to kind of figure out how to. So it's a little more complex. It's a little bit of R with programming and web page stuff. So I'm not real proficient in that. But. Okay, so I think we'll stop there for today. So.
Thank you.
Yep.
Thank you.
You made it.
See you next week.
Yeah.